So, we've now derived the Dirac equation. Before discussing the solutions to the Dirac equation, we'll discuss what it did not achieve, what the Dirac equation did not achieve. Because if we compare the definition of the Hamiltonian in wave mechanics, so I dt, the time evolution of a wave function is obtained by the Hamiltonian acting on the wave function. If we compare this definition of the Hamiltonian with the Dirac equation, which is I dt acting on the spinner psi t comma x is equal to minus I alpha dot nabla plus beta m psi. We see that for the Dirac equation, the Hamiltonian is nothing but minus I alpha dot nabla plus beta m. Now, the trace of the Hamiltonian will give us the sum of the eigenvalues. But the condition that the matrices alpha and beta are traceless therefore means that the eigenvalues of the Dirac Hamiltonian must sum to 0. So the trace of H Dirac is equal to 0. So if we have a positive energy solution, then there's also a negative energy solution. Remember that the eigenvalues of the Hamiltonian are the energy levels for the wave equation, for the solutions to the wave equation. Now this means that we will get negative energy solutions also to the Dirac equation. But Dirac set out to get rid of the negative energy solutions to the Klein-Gordon equation and didn't achieve that. The Dirac equation does achieve something else that we will celebrate later. But let's first discuss the problems with the energy levels. So Dirac, of course, realized this early on and proposed a solution to the problem, which has become known as the Dirac sea. So the Dirac sea is to accept solutions with energy less than 0, but say that the vacuum state is that with all states with negative energy already occupied. What we'll see is that the Dirac equation describes the motion of spin half particles or fermions, and therefore, if the negative energy states are already filled in vacuum, then the fermions cannot occupy them. Again, that would be double occupancy and in contrast to the Fermi principle for fermions. So as the negative energy states are already full in vacuum, the Pauli exclusion principle will forbid any positive energy electron to fall into one of the negative energy states. However, if energy is applied to the vacuum, then an electron can be excited from a negative energy state to a positive energy state, and a hole, an electron pair, is created. The absence of the negative energy electron, i.e. the hole, is interpreted then as the presence of a state with positive energy and positive charge, that is the anti-electron, also called the positron. Right? So essentially, vacuum is full of negative energy states, and if you transmit enough energy into the vacuum, then one of these already filled states can be excited to a positive energy, and the hole left over is interpreted as an antiparticle. In this way, Dirac predicted the existence of the positron before it was discovered. Back then, it only took 5 years between prediction and discovery. Now, this is a very good argument as long as you deal with fermions. But of course, it wouldn't work for bosons, right? That could have double occupancy. So, a consistent solution for particles of any spin, a consistent interpretation of wave dynamics for particles of any spin is provided by quantum field theory in a picture that was first developed by Feynman and Stückelberg, where positive energy particles can travel forward in time and negative energy particles travel backwards in time, e to the minus I et. Good. So in this way, negative energy particles with momentum p mu traveling backwards in time because it's negative energy is reinterpreted as a positive energy antiparticle with momentum minus p mu traveling forward in time. So let's see, first we have the Dirac C, and then we have the time-ordered perturbation theory. By Feynman and Stückelberg. So what they're saying is that positive energy solutions travel forward in time, negative energy solutions travel backwards in time, and a positive energy particle, a negative energy particle with momentum p mu, it will travel backwards in time, is reinterpreted as a positive energy particle, antiparticle, with momentum minus p mu traveling forward in time. We'll see how that naturally arises in a picture here, where let's take first one studies non-relativistic scattering. So if one has a space-time diagram of time and x, where one studies, for example, E mu scattering, where one has an electron scattering off the potential from a muon. So the muon has an electric potential and the electron scatters on that potential. Now, in non-relativistic scattering, the force is traveling at infinite speed. It's felt immediately. Now the horizontal axis here presents the time at which a elementary process happens, and in non-relativistic mechanics one pretends that the photon travels at infinite speed such that you get essentially a reaction at a distance. Now obviously that's not how we do quantum field theory, and that's not how we do relativistic mechanics, but that's the picture in non-relativistic mechanics. Now, in time-ordered perturbation theory, one would instead say that two processes occur, time and x, one in which the electron comes in. The electron will emit a photon traveling forward in time that will scatter off the muon. So that's one possible time ordering of the electron scattering off the muon. But there's of course another time ordering. Which sees the electron coming in, and at this time, T2, it emits a photon with negative energy that travels backward in time and hits the muon. Now this might sound crazy, and indeed if we watch the situation from the muon, then it's the muon emitting the photon that later hits the electron. Now, of course, the time ordering of events is not a Lorentz invariant when the two events are spatially separated, are separated with a larger x distance than ct distance. Space-like separated events don't have the same time ordering in all reference frames. So often we will actually use Feynman rules in momentum representation which aren't located in x, and then the time ordering is irrelevant. That's how we do proper quantum field theory. We don't have to think about the time ordering when we use the Feynman rules. Having arrived at the Dirac equation, we will now investigate in some details the solutions and indeed show that they correspond to spin up and spin down states of the fermion and antifermion. So the Dirac equation written in momentum space is gamma mu p mu minus m times the identity matrix in spinor space psi of p is equal to, in Dirac notation we write the same thing, p slash minus m psi of p, and the Dirac equation says that this must be 0. Now we'll take a little time now to discuss in more details the symbols. We have that the gamma mu are determined in terms of the alpha i's, which are the matrices 0, sigma I 0, and beta is the 2 by 2 identity matrix arranged like this. This is the Dirac representation of the gamma matrices, where then we have gamma 0 is equal to beta, and gamma I is beta alpha I. Now sigma I here are the Pauli matrices that I will discuss shortly, but for now just think of them as 2 by 2 matrices called the Pauli matrices. So this means that gamma I, let's write down what gamma I is. Gamma I as beta alpha I is 1, 0, 0, minus 1 times 0, sigma I, 0, which is 0, sigma I, minus sigma I, 0. Now, this means that the Dirac equation can be written as P0 if we write out the terms in the contraction gamma mu p mu. We then get a Dirac equation saying that P naught times gamma naught plus Pi gamma I, Pi low, gamma I up, minus M times the identity matrix, all acting on psi of P must be 0. Now, since we have here a structure of matrices which is block 2 by 2, we will speculate that we can find the solutions, or the plane wave solutions, on the form psi of P is psi of P, a 2-column matrix, phi of P, a 2-column vector, sorry, e to the minus I px. Now, in this Dirac equation, we have to find now Pi gamma I, and we have Pi gamma I is equal to, we just plug in what gamma I was, remembering here that gamma I is 0, sigma I, minus sigma I, 0, and of course Pi it has a sign because I is lower as the covariant vector. So what we get here is 0 minus sigma I Pi up, sigma I Pi up, 0. So that means that the Dirac equation, as written here, in terms of the components psi and phi, we just write out, if we plug in the form of psi here, in terms of psi and phi, we get that P naught psi of P minus sigma of P phi of P minus M psi of P must be equal to 0, and therefore that sigma of P on phi of P must be P naught minus M psi of p. Good. The Dirac equation for phi, the lower components on the 4-spinner, is instead that minus p naught phi of p plus sigma dot p psi of p minus m phi of p is equal to 0. That's simply what you get from the lower half here, p naught minus 1 times the lower phi plus the contribution from pi gamma I minus m times the identity. Good. So therefore, sigma dot p on psi of p is equal to p naught plus m phi of p. Now, the Pauli matrices have a nice identity here. Let me just write out a bit about the Pauli matrices. Now, the Pauli matrices are defined by sigma 1, 0, 1, 1, 0. Sigma 2 is 0, minus I, 0, and sigma 3 is 1, 0, 0, minus 1. And the vector of Pauli matrices is defined as the collection sigma 1, sigma 2, sigma 3. Now, they will have the property, which you can easily check with this representation of the Pauli matrices, that the anti-commutator of sigma I and sigma j is 2 delta ij times the identity matrix, and the commutator of 2 sigma I comma sigma j is 2i epsilon I jk sigma k. Now, with this relation here, the anti-commutator will turn out to be useful to calculate the allowed energies P naught for the solutions parameterized in terms of psi and phi. So in order to find out what P naught is, we use the identity or the result that sigma dot p squared is equal to p squared. That's very easy to see because sigma dot p is sigma I pi, so sigma dot p squared is sigma I pi sigma j pj, but this is all index notation, so we can commute things here, and what we get is that sigma I sigma j is half delta ij, right? So we only get a contribution from the sigma I sigma j when I and j are identical. We only have it once, and when we only get something when it's identical, it means that we get, and then we get the identity, is that we get p squared. Good. So if we use that, we can find the allowed values for p naught, because we simply let sigma dot p act on these equations we've arrived here and there. So letting sigma dot p act on the equation for phi here first, we find sigma dot p acting on sigma dot p on phi is equal to sigma dot p of what was on the right hand side, which was p naught minus m psi of p. But we can commute through the sigma dot p and we get simply p naught minus m sigma dot p on psi of p. But sigma dot p on psi of p was p naught plus m. So what we get here is p naught minus m, p naught plus m phi. We can write that out as p naught squared minus m squared phi of p. So therefore, p naught squared, and here we had that this is equal to p squared phi of p. So therefore, p naught squared on phi is equal to p squared plus m squared on phi. Good, so the energy is m squared plus p squared. That's really good. One could do something similar for the psi. What one finds there. So one finds that E squared is equal to P squared plus M squared for the plane wave solutions to the Dirac equation in terms of phi. One could do the same calculation here with psi and arrive at the same result. P naught squared is equal to P squared plus M squared. Now, of course, that means that P naught, the energy, is plus or minus the square root of P squared plus M squared, all consistent with the solutions of the Dirac equation also solving the Klein-Gordon equation. Now, if we consider the solutions in the rest frame of the particle, consider the solutions in the rest frame where P is equal to 0, then for a massive fermion we find that P naught on psi is equal to m times psi. Simply from the equations up here. If the momentum is 0, so that the left hand side here is 0, then we get P naught is equal to minus m phi. Or here, the left hand side is 0, so P naught minus n on psi is equal to 0. P naught plus n on phi is equal to 0. So one gets P naught on psi is equal to m psi, and P naught on phi, however, is equal to minus m phi. So at rest, the energy of psi is equal to m psi, and the energy P naught on phi is minus m phi, less than 0. So positive energy solutions let's call them phi plus at p equals 0 must therefore have phi equals 0, and the negative energy solutions let's call them psi minus for p equals 0 must have psi, that's not a nice one, psi equals to 0, such that for the force spinner, phi plus the positive energy solution at rest is equal to psi 0 e to the minus I mt, there's no p, and the negative energy solution at p equals 0 is 0 phi e to the I mt. So that was the solutions for the particles at rest. If they are not at rest, the solution is still dictated by what we found up here, that sigma dot p phi must be p naught minus n on psi, and sigma dot p on psi must be equal to p naught plus n on phi. So they dictate the solutions when the momentum is different from 0. And what one then finds is that for p non-zero, the positive energy solution is equal to some normalization constant that we'll find, psi sigma dot p for e plus m psi e to the minus I p dot x, which we'll call or define as u of p, a spin of p, e to the minus I p dot x, where p naught is the energy, is p squared plus m squared square root. Now the space here is spanned with the space of solutions spanned by this psi r can be 1 or 2, and n is a normalization that's conventionally chosen such that of the two choices of u dagger r of p, u s of p is twice the energy, but only when r is equal to s and 0 otherwise, which gives that the normalization constant is the square root of e plus m. Now the spinners psi 1 and psi 2 cover the 2 degrees of freedom that is left in the solutions. We'll see that they correspond to the spins, but we'll see that later. So psi 1 is simply 1, 0, and psi 2 is 0, 1. So that's the positive energy solutions. For the negative energy solutions, are usually written as psi minus R is a normalization constant, and then we had it has to be equal to sigma dot p over E plus m of phi r and phi r e to the IPX, which we define as VR of P e to the IPX, where P naught is the energy. And again, phi here, there are 2 degrees of freedom. There's a phi 1 1, 0, and a phi 2 0, 1. And the full solution space is spanned by those 2 degrees of freedom. Now, the spinners U, P, and V of P represent particle and antiparticle solutions with momentum P and energy on shell as E equals square root P squared plus M squared. Let us now consider the spin and the helicity operators for the solutions to the Dirac equation. First, spin. As we've seen, each Dirac spinner, this is right here, spin and helicity. Each Dirac spinner has 2 linearly independent solutions, which we stated earlier corresponded to the 2 possible signs or states of fermions, spins of fermions. We'll define here the corresponding spin operator. But let's start by considering a particle, not antiparticle, but a particle at rest. So we've got one solution, U1, for the spinner, which is 1, 0, 0, 0. And we've got another solution, U2, which is 0, 1, 0, 0. Now, these 2 spinners have eigenvalues plus and minus a half of the operator or matrix, a half sigma z 0, 0, 0. One can just test that directly by saying that a half sigma z 0, 0, 0 on 1, 0, 0, 0. Plug in the sigma z Pauli matrix and find that this is a half 1, 0, 0, 0. And if one plugs in the 0, 1, 0, 0, one gets minus a half when using the sigma z Pauli matrix. Now, one can repeat the same exercise for antiparticles with a VI. So one gets V1, 0, 0, 1, 0, and V2, 0, 0, 0, 1. And one finds that the spin operator calculates or extracts the spin of the fermions, of the Dirac spinors, is S equal to a half sigma. That's the one that works for the particles, and the one that works for the antiparticles is sigma as well, but in the lower right corner. So I say that that's a spin operator. Well, it gives us the eigenvalue a half when operating on the states, plus minus a half. What else do we need the spin operator to do? Well, when we square it, it needs to give us 3/4. We can check that explicitly. S squared is equal to S times S, which is a half sigma 0, 0, sigma times a half sigma 0, 0, sigma, which is a fourth sigma 0, 0, sigma, sigma 0, 0, sigma, which is a fourth sigma squared 0, 0, sigma squared. Now sigma squared is sigma 1 squared plus sigma 2 squared plus sigma 3 squared, right? It's the square of each component in the sigma, which is the vector sigma 1 comma sigma 2 comma sigma 3. But this thing here is equal to 3 times the 2 by 2 identity matrix, right? Because we know from the Pauli matrices that sigma 1 or sigma I squared is the identity matrix. We get that 3 times. So what we get here is 3, such that here we get 3/4 times the identity matrix, like this. Good. So the spin operator behaves as we expect the spin operator to behave. Now, therefore, for the particles at rest, p equals 0, the top two components of psi plus describe fermions with S set. Projection equal to a half, that is called spin up, and S set equal to a minus a half, which is called spin down. So, for particles at rest, the two top components of psi plus, which we previously called psi, and it has two solutions. So I'll describe fermions with SZ equal to plus a half, psi 1 equal to 1, 0, and SZ equal to minus a half, which is psi 2 equal to 0, 1, respectively. This is all in the Dirac representation of the spinors. One can find other representations based on other representations of the gamma matrices. Now, in the case of an arbitrary momentum P, it becomes interesting to consider the projection of the spin operator along the direction of the motion of the particle instead of considering along the z-axis. We consider it along the axis of the direction of motion of the particle. That's P divided by length of P. This is called the Helicity Operator. And we define it as h of P is the spin projection along P divided by P, to make it depend only on the spin and not the momentum length. Good. Now this operator, as you can easily check using the identities we've already used for the power matrices, satisfies that h of P squared is equal to 1, because sigma dot P times sigma dot P is equal to P squared. So therefore, its eigenvalues must be plus or minus 1. So the Helicity operator, which measures the spin projection along the direction of motion, has eigenvalues plus or minus 1.